Greetings, physicists. This video will be about solving resonance inside of pipes. And we'll look at a couple types. So we're looking first at your eardrum. And if I'm drawing your ear, so there's this outside funnel piece. And there's the ear canal inside, and then there's the eardrum itself. And of course it keeps going. It connects to the hammer anvil stirrup. I forget the actual name of the organs. But we're going to claim that that eardrum is about 2.5 centimeters for an adult. And we're going to claim that sound traveling through your ear canal travels about 350. And we're looking for what frequency can we get out of your eardrum. Well, let's see here. Well, this is definitely a closed pipe, so I'm going to redraw your eardrum like this, where the open end is the outside of your ear towards the air, and the closed end is the eardrum itself. And so it says, what sounds can we put in there within the range of human hearing? Let's start with the fundamental. A closed pipe does a shape like this for the fundamental, which is 1/4 of a wave. So that length of the eardrum will be equal to a lambda divided by 4. Okay? And let's look at the other equation we're going to need. So we have V equals F lambda, which would be equal to F times 4L. If that makes sense. And so if I rearrange that, because what I'm really looking for is frequency, hang on, we will get frequency equal to V over 4 times the length of that ear canal. Now I have meters and I have centimeters, so I'm going to change those units, right? On top it's going to be 350 meters over seconds. And on bottom it's going to be 0.025 meters. So let's get a number there. Calculator, 350 divide 0.025. Big numbers. See if those make sense. Oh, I forgot to put the 4 in. Silly. I have to multiply that by 4. And actually, I'm not going to have to put that in a calculator if I do that, right? Because 4 times 0.025 is just 0.1. Yeah. So divide by 0.1 and you multiply by 10. So that's 3,500 meters. Sorry, seconds. Hertz. The meters part cancels. And I get 1/seconds or hertz. So that is the lowest. That is the fundamental frequency that your ear can pick up. 35, well, not that your ear can pick up, but that resonates within your ear canal. So 3,500 hertz, that's definitely within your hearing. Remember, you can hear down to about, you can hear down to about 20 hertz and up to about 20,000 hertz. So that definitely resonates in your ear canal. And then we can go up from there. Now, because it's a closed pipe, the fundamental frequency is 1. The next frequency that fits is actually frequency 3. We skip 2. We only do odd numbers, and so I have to multiply this by 3. So I would get the next frequency would be 10,500 hertz. That's still within my range. And then I would go up to 5, so another 7, so that would be 17,500 hertz, which is also within my range. And if I add another 7,000, to go up to 7, I would be at 24. That would be outside my range. So there's 3 frequencies that resonate within the ear canal by itself. Now, that's different. I mean, we're talking about like this shape wave fitting in here and making itself louder. So you might be sensitive to that particular frequency, but all the other frequencies in between will still cause your eardrum to vibrate, and you would still hear them. Otherwise, yeah, we would only be able to hear 3 different pitches, which would be weird. All right, so that is that problem. Let's move on here. Okay, we got a flute and a clarinet. If you are not familiar with them, here is a flute, but it has like a hole here and little finger holes all the way down. But like you blow air across this hole here, and then the clarinet has this like pointy mouthpiece and a bell at the end, little keys all over it, little down the way. This is a good drawing here. All right, they are about the same length long, true story. But the clarinet can play way lower, much lower, octaves lower than the flute can play. And why would that be the case? Well, let's think about that. The flute, when you blow into it, the mouthpiece is open. So here's the mouthpiece. There's like a hole that you blow across. So when waves resonate back and forth, like this, you get the fundamental frequency, frequency 1, is lambda over 2. But when you do that same note on a clarinet, the clarinet's mouthpiece is closed. So it does one of these. So the fundamental frequency on a clarinet is equal to lambda over 4. Well, if we draw those waves out, this wave that's already half of it, it only goes 1/2 more. This wave goes half more, and then again, and I don't even have room because I drew it too big. So that's a bigger wave that fits inside the clarinet's fundamental frequency than fits inside the flute's. So by a factor of 2. So the clarinet, if it were exactly the same length as the flute, would be able to play almost twice as low as the flute. Or, yeah, if it were exactly, it would be exactly twice as low. Or twice as large a wave. Okay. So we're trying to study frogs here, and we make a tube and fill it up with water, and we put a mic at the bottom. That's going to create pressure and standing waves, which, because there's pressure waves, they are sound waves. And we have a couple questions. What is the fundamental of this water-filled tube? And then if we were to put frogs at a certain point, what's the weakest note they could hear? No, what does it say? What is the lowest frequency that would result in a node? Oh gosh, that's going to be tricky. All right. So here we go. The only number they gave us is 1.4 meters. So let's do that. We'll draw the tube. We have this vertical tube filled with water. So we fill it all the way up. Filled with water. Let's make it blue. There you go. And a little microphone down here that makes sound waves like that. They travel up and down the tube, and it says that the bottom is an antinode and the top is a node. So that's this. So this is a closed pipe. It's just a closed pipe filled with water. And so you could look this up, but the speed of sound in water is 1480, I believe, meters per second. I mean, it depends on the temperature and everything, but let's just say 1480 is fine for this problem. And we know that the length of the tube is 1.4 meters. So they say, what is the fundamental frequency? Well, the fundamental frequency be V equals F lambda, but again, lambda here is going to be equal to lambda over 4 is the length of the tube, right? Because this is a fourth of a wavelength. So 4 lambda, or 4L. So we'll have V equals F times 4L. And if we're trying to solve for frequency, divide by the 4L. And we will get V over 4L is the fundamental frequency of that tube. So let's plug that in. The V was 1480 meters per second. The tube is 1.4. See, this is nice, right? 1480, whoops, over 1.4. So this should be pretty close to 1,000, I would think. It's not going to be exact, which is why I'll put it in the calculator. Yep, equal to 1,057 hertz. And it looks like a 2 sig fig problem, so this is like actually 1,100 hertz. Let's keep that. All right, so everything's going to be multiples of 1,100. And then we put the frog at 0.28 from the bottom. What is the lowest frequency that would result in a node at this point? All right, let's go do this down here where I have a little more room. So we have a big tube. Again, this whole distance is 1.4. And this distance is 0.28. And I need a node there. So there always will be an antinode here, and there always will be a node here. So essentially, I have to pick a wave that hits here and then bounces back and makes it all the way to the end perfectly. Well, I'm curious if 1.4 and 0.28 divide evenly, because essentially, if that's true, then 0.28, 0.28, 0.28, I would just count how many of those I have to go. So let's see if that's true. 1.4 divided by 0.28 is a perfect, 5. So 1.4 over 0.28 equals 5. So essentially, this is the first of 5 tick marks. One, I drew, so I need one more in here. So let's redraw this. One, 2, 3, 4, 5. So that would be perfect divisions of 0.28. So I'm going 1, 2. Hold on. Is that right? Yeah. 3, 4, 5 nodes. So let's try to figure out what harmonic we are at. Okay, so we have the fundamental, which has one antinode and one node. The next one up is going to have two nodes, right? So essentially, with only one node is here, with only 2 nodes is here, but we know that this is the fundamental harmonic. This is the third harmonic. So every time we add a node, we're going up by 2 harmonics. So I can just count this. So this is first, third, 5th, 7th, 9th, 11th harmonic. And I told you my fundamental frequency here, this one, we just calculated was 1100 hertz. So if I go up to the 11th harmonic, it's literally 11 times the fundamental frequency. So 11 times 1100 hertz. Well, 11 times 11 is 121, and I'm going to add those 2 zeros at the end. So 121.00 hertz. So pretty high frequency. Still within the range of human hearing. Although I don't know if that's true in water. Yeah, no, it wouldn't matter. So there you go. Hopefully this is helpful to you in solving problems with open and closed pipes.